So this video is for the Lesson 8 Ready, Set, Go problems in Unit 2. So these first problems on the Ready side, we are writing explicit equations for tables and graphs. So just a quick reminder that if we know that we have a linear equation, we can write a linear equation in the form of y equals mx plus b, where m represents our slope or our constant rate of change, and b is the y value of the y-intercept. Now, if we don't have the y-intercept, we could write the equation differently. And then for an exponential, we said this one is for linear. Linear. For an exponential function or equation, we could write the equation in the form of y equals b times g to the power of x, where b still represents the y-intercept, so 0, b would be the ordered pair, and g represents the growth factor. And remember, when we talked about geometric sequences, we often call that the common ratio. Okay, so in number 1, I can see that this is a linear function, and I could see that because as x increases by 1, I could see that our y values, or f of x values, are decreasing constantly by 7. So that's how I know it's linear. I also know that -7 is going to be my slope or constant rate of change. Since I don't know the y-intercept, I could write the function using different values in the table. So I could say f of x equals, I'm going to still use this form up here, except instead of just x, let's say that I use this first ordered pair. So I would have -7. Since I'm starting at 2, this would be x minus 2, and then -4 or -4 would be my constant. Or another option is we could work backwards and figure out what our y-intercept is. So when x is 1, for example, if I go back and I think what y value would have to go here, well, -4 plus 7, if I'm working backwards, would be 3. And when x is 0, if I work backwards and add another 7 to that, I would have 10. So I could also say f of x equals -7x plus 10. And if you were to distribute this -7 to this expression and then combine like terms, you should end up with this equation anyway. All right, in number 2, I could tell that this represents an exponential equation, and I could tell that because as x increases by 1, my table is not changing by a constant number. In other words, I'm not adding or subtracting a constant, but instead I see a multiplication pattern. And it's easiest for me to spot here that I know 2 times 5 is 10, 10 times 5 is 50, so it must be true that 2/5 times 5 is the whole number 2, which it is. So since I already have the y-intercept in my table, I could follow this form of my exponential equation and say f of x, remember f of x is the same as y, it's just we're using function notation instead of y notation. F of x equals, well, my y-intercept was 2, and my growth factor, or my common ratio, is 5. So I could write my equation like that. Again, like we've done before, you could write the equation using a different value in the table. So like, let's say I use this ordered pair instead. If I start with the value 10, I would still have that common ratio or growth factor of 5. But since I'm using a value when x is 1, I would have x minus 1 as my exponent. Okay, we'll do the rest of these a little bit faster. So in number 3, as x is increasing by 1, I can see that y, or f of x, is decreasing by 24 each time. Nope, it's not. I just caught my own mistake because I was like, wait a minute, negative 48 minus 24 is not negative 96. So it's okay to make mistakes. We've just got to make sure we catch them. It turns out that we're doubling each time. Maybe you caught that one. So negative 24 times 2 is negative 48. When I multiply that by 2, I get negative 96. And then again, if I double that, I get negative 192. So again, I could use, so that means this is exponential since we see a pattern of multiplication and we have a growth factor. We don't have a constant rate of change. So I could write my equation like this. I could really pick any ordered pair from my table. So like, let's say that I use this first ordered pair. If I use the starting value of negative 24, so I'm not really using b, where that's my y-intercept, but I'm using a different y value for when x is equal to 2. I'll have my growth factor of 2, and then instead of just the exponent x, I will have the exponent x minus 2 up there since I used the second x value. Now, just like before, we could go back and figure out what our y-intercept is. So like if I go the opposite direction in my table, I could see a pattern where I'm dividing by 2. So when x is 1, y would be negative 12. When x is 0, y would be negative 6. And that would be my y-intercept. So I could also write this as f of x equals negative 6 times 2 to the power of x. All right, number 4. I noticed that my x values are negative, but that's okay. They're still increasing by 1, so it makes it easy for me to see when they're increasing by 1 that this is, again, an exponential relationship because my growth factor is 1/3. And I know sometimes students want to say that we're dividing by 3. Well, that is correct. We are dividing by 3, but I would think of my growth factor as a multiplier. So if you forget how to identify our growth factor, it's the same as our common ratio. Take 2 consecutive outputs from the sequence and divide 1 by the one before it. So what I mean by that is if I start at 3, I could divide 3 by 9 to get 1/3. Or if I start with 9, I could divide by the number before that, 27, to get 1/3. Okay, so again, it might be easiest just to figure out what our y-intercept is, but I can write my equation using any number in this table. So let's say that I use the negative 1, 3. If I use that ordered pair, if my starting value is 3, my growth factor is 1/3, but instead of this being just an x, this would be like x minus negative 1. And that would be the same as 3 times 1/3 to the power of x plus 1. But if I want to just continue my table out one more number where x is 0, and if I multiply 3 by 1/3, sorry, I'm going to go back and erase this so I have space. Oh, maybe not. It won't let me. If I do that though, 3 times 1/3 would be the number 1. So like my y-intercept would be the point 0, 1. So I could also just write f of x equals 1 times 1/3 to the power of x. And that's the same as just 1/3 to the power of x. All right, in number 5, now we're working with some graphs, and I can see with my eyes that this graph is linear because it's a line. And I can see on the graph my ordered pair for the y-intercept is the ordered pair 0, 2. And I could find my slope by using rise over run. So on a graph, sometimes we call this rise over run, but it's essentially our change in y divided by our change in x. So if I pick one other really good point, let's say I use this point, I could say that my rise, because I'm always going to move from left to right, so my rise is negative 1, and my run is 1, 2, 3, positive 3. So my slope, or constant rate of change, is negative 1/3. So every time x increases by 1, our y values decrease by 1/3. So using our y equals mx plus b form, I would get negative 1/3 x plus 2, or 2 minus 1/3 times x. All right, in number 6, I can see this is an exponential function. And again, I could see the y-intercept on my graph is the ordered pair 0, 1. And even though only every other number on the y-axis is labeled, I know that the y-axis is labeled with even increments. So if it helps, I could fill in the missing numbers there. And then I need to figure out what my common ratio is. And so let's say I pick my next ordered pair. When x is 1, I have this ordered pair 1, 4. And I need to just remember that when I have an exponential relationship, I'm multiplying. So if I start at 1 and I multiply by a number to get 4, well, the number I'm multiplying by must actually be the number 4. So my growth factor is 4. And the y value of my y-intercept is 1. So I could write this in the form of y equals b times g to the power of x. And that's the same as just 4 to the power of x. All right, so let's see. That was number 6. Number 7, we'll do these a little faster. We've got another linear. Our y-intercept is 0, 1. Our slope, we're going down 1 every time x increases by 1. So my slope is negative 1 over 1, which is negative 1. So I could write this in the form of y equals negative 1x plus 1. And that's the same as just like negative x plus 1 or 1 minus x. For number 8, ooh, this one's a little tricky, so I'm going to be careful. I'm not sure that right away. This looks like my y-intercept is 1/2. I don't really want to guess, but I can tell I've got a clean ordered pair here at 1, 1. And then let's see, when x is 2, y is 2. And then when x is 3, y is 4. And like, if it helps you, you could make a quick table out to the side. That helps me a lot. So I'm going to leave room for my value when x is 0. But I know that when x is 1, y is 1. When x is 2, y is 2. When x is 3, y is 4. So again, if I'm thinking like, what am I multiplying by in my table? Well, I'm multiplying by 2. So that's my growth factor, and that confirms for me that this must be where y is 1/2. So I could write this in the form of y equals b times g to the power of x. So 1/2 times 2 to the power of x. Or you could write it from ordered pairs that we had without finding the y-intercept. So like if I use 1, this first ordered pair at 1, 1, my growth factor is still 2, but I would have an x minus 1. All right, and then number 9, again, this is linear. I could see my y-intercept is 0, negative 4. And to figure out my slope, I'm going to use this other point here at when x is negative 1. So if I do rise over run, my rise is, let's see, I'm going down 1, 2, 3, 4. Since I'm going down, my rise is negative, and then I'm running to the right a positive 1. So my slope is negative 4 divided by positive 1, which is just negative 4. So in y equals mx plus b form, that's negative 4x minus 4, where that second minus 4 or negative 4 is from our y-intercept. All right, so those are the ready problems. Let's talk about the set problems. I think this first problem might be a little bit tough, but number 10, the balance in an interest-bearing account. So that's going to be like a financial account where money is being probably earned. It's not actually very clear from the problem. The balance in an interest-bearing account is modeled with a continuous function over time. Which of the following domain choices is a possibility? So even if we don't know what an interest-bearing account is, we do know that continuous functions, unlike discrete functions, should be something that we could model with a set of all real numbers. And so if this function were discrete, then choices like B, C, and D might make sense because we define discrete functions as functions that have a domain that is like a subset of the set of real numbers. So the choice for this is going to be A. And the reason that we would specify that the domain is real numbers greater than 0 is that when we start modeling this, since it's a function over time, we would likely begin examining this function when time is equal to 0. So I would actually say real numbers greater than or equal to 0 is probably a better answer, but of the answers we have, A is the best choice. In question 11, select the only equation that can be used to model a continuous exponential function. Okay, so let's take these one choice at a time maybe. Choice A is out for 2 reasons. So I can tell from the way this is written that this is a recursive function. And a recursive function we would use for a discrete function, but I could also see that we are multiplying our previous term, I'm going to write PT for previous term, f of x minus 1, by some value b. And so if we're multiplying, actually I take that back, if we're multiplying this would be exponential, so never mind, this is only out for one reason. It's not the issue that we're multiplying, the issue is that this would represent a discrete function, so we really cannot use a recursive equation to describe a continuous function because we can only input integer values for x in a recursive equation. Okay, B is going to work for us. B is going to be the correct answer here, and I could tell that this is in the form of, I realized in the text they're using A and B instead of B and G, but this is in the form of like y equals our y-intercept times our growth factor to the power of x. And again, when that says x minus 1, that just tells us that this value here is not actually our y-intercept, but it's the output when x is equal to positive 1. All right, C is out. We said A is out. C would also be out because that is a equation in slope-intercept form, but that would model a continuous linear function. And D is out because, again, it is recursive and we're adding something to our previous term. So that would model a discrete linear function. We said the top one was discrete exponential. This one is just plain old exponential continuous. And this one is linear and continuous. These are tough questions, I'm not gonna lie. All right, number 12, select the only equation type that could be used to model a continuous linear function. Okay, so since again we're talking continuous, let's go ahead and rule out the 2 function or equation types that are recursive. And that's gonna be A and D. And the way I know these are recursive is that I'm modeling in A f of x using f of x minus 1, so that would be like my previous term, and then I'm given a starting value. So this top one would be a discrete exponential. This bottom one, because we're adding, would be a discrete linear function, but they're both discrete, not continuous. So the correct choice here is C. Again, this is in the form of y equals mx plus b, whereas this is in the form of y equals our y-intercept times our growth factor to the power of x, or in this case, x minus 1. All right, 13, the domains of arithmetic and geometric sequences are always subsets of which numbers? Since we're talking about sequences, we are now talking about discrete functions. So remember, an arithmetic sequence is a discrete linear function. A geometric sequence is a discrete exponential function. So in our real number system is going to include numbers that are irrational, such as like pi, for example. And I can't have like a pith term in a sequence. So real numbers wouldn't work. Rational numbers would include numbers like 1/2, or really any number that could be represented with a fraction. So rational numbers also would not work. That is too large of a set, because I can't have a half term in a sequence. I could think about a half term, but sequences increase by whole numbers. So really, we're looking at the subset of integers here. And we said integers are defined as like whole numbers and their opposites. So like -3, -2, -1, 0, 1, 2, 3. Those are all integers. And if I discard the negatives and start at 0, those are all whole numbers. And I would say typically sequences have a domain of whole numbers, sometimes just, or maybe even more often, a domain of natural or counting numbers, and that is when we exclude 0 from the set of whole numbers. All right, number 14, select the attributes that characterize both arithmetic and geometric sequences. Select all that apply. Okay, so they are not continuous, but they are discrete. Because again, in a sequence, I don't have a half step. I go from my first term to my second term. There's not a half term. All right, some of this is written in function notation and, set builder notation, I mean. So in option C, and I'm not too worried about set builder notation, but in option C, this is saying that our domain would be the domain of natural numbers, and that is correct. This is saying the domain would be the domain of real numbers, and that does not work for a sequence. Let's see. We could definitely use a recursive rule. I know I'm going a little bit out of order, I'm sorry. We could use a recursive rule to characterize geometric and arithmetic sequences, or at least that is something we can use with arithmetic and geometric sequences since they are discrete. We don't typically have negative x values in one of these sequences. We could imagine like a negative term in a sequence, but it doesn't make sense. When we talk about terms, we usually are talking about counting numbers. I think F is just kind of confusing. I don't think this choice makes a lot of sense, but I'm going to go with it. Something constant or consistent. Well, what I think this means, although I think this could be written a lot better, is that a constant might be like a constant rate of change. So like in a sequence, if I'm adding 4, or it could be like a constant or common ratio. So like, let's say I'm multiplying by 2 in my sequence, I would call that the common ratio. But I don't love the way like any part of this question was worded, and that's just my personal feeling. So, okay, let's see. Number 15, explain why arithmetic sequences are a subset of linear functions. What makes them different? Well, if you just think of any linear function, we said that a constant or a continuous function rather, that I would connect all of the points like when I graph it. But if I'm talking about an arithmetic sequence, I'm usually just going to be using inputs that are whole or natural numbers. So either starting at 0 or starting at 1, but I would use whole or natural numbers for my domain. So so when we say a subset of linear functions, it's really the domain restriction. So I would say that sequences have a restricted domain and that's usually either just all whole numbers or all natural, or sometimes we call them counting numbers. So like numbers you count with, 1, 2, 3, 4, so on. Well, I'm going to just say for number 16, the same reasoning applies here. So like if I, sorry, my color scheme is changing. If I consider a continuous exponential function, well, a geometric sequence would just be points that exist on that function, again, when we have a restricted domain. So honestly, I really think this is the same answer here. I suppose we could state more in questions 15 and 16 about how those sequences relate to their functions, but I really think the reasoning is the same for 15 and 16. All right, number 17, the equation y equals negative 4x plus 32 has many solutions. Some of them are, and we're given 3 ordered pairs, 0, 32, 3, 20, and 5, 12. How can this equation be represented to show all possible solutions for the equation, and explain how the representation shows all solutions? Well, the best way to show all solutions is with a graph. So we could graph the equation y equals negative 4x plus 32. And I'm just going to sketch like what that could look like. 32 is a positive number. Negative 4 would be our slope. So like, let's assume that this line I just drew goes through the y-intercept at 0, 32. And has negative 4 as its slope, so like down 4 over 1. And so the graph, the reason that represents all solutions is that we connect the points. So we form a line on the graph and we use arrows to show that our graph continues in both directions. In number 18, the equation y equals 5 times 2 to the power of x has many solutions. We're given some ordered pairs again. Again, I think this is kind of getting at the same thing as number 17, that the best way to show all of the solutions is by graphing y equals 5 times 2 to the power of x. So again, in this graph of an exponential function would have a y-intercept at 0, 5, a growth factor of 2, meaning that like as x increases, we're multiplying by 2. Going the other direction, I could think of multiplying by 1/2 as I go to the left, or dividing by 2. And again, by connecting, like not just plotting points, not just plotting the point 0, 5, or 220, but by actually connecting those values. Okay, sorry, I lost my train of thought for a second. I thought there was a mistake, but there's not. Okay, so by connecting those values, we could show all of the solutions. Because remember, like y equals 5 times 2 to the power of x, we could find a solution when I plug in like 1/2 for my value of x. So the best way to represent this is with a graph.